Hello and welcome to this video. Today I want to talk to you about a very interesting case when you have two rigid bodies connected as at a joint that allows rotation. Um, this is you probably heard of it as an intermediate hinge or a pin connected connecting two rigid bodies. So this is, for example, like a piston. You can see when this moves up and down, this piece is connected to this piece and it rotates about this joint. There is very common structures that will include this internal pin or internal intermediate hinge. Look at this bridge, for example. You can see that this side is continuous, and then there is like a hinge or a pin here. Same thing from the opposite side, and this can be modeled as intermediate hinge, and supports on both sides. So let me show you some application to what this actually means. Look at this bridge here. There is a continuity from the right hand side, continuity from the left hand side, and then you see this hinge. And if you look closely, it looks something like this. One side is sitting on top of the other. Um, this is the basic simple beam that we've been working with. This is a continuous beam. It's statically indeterminate. So we'll deal with it and towards the end and see how we can work our way through it. This is the intermediate hinge that I'm talking about. So I want to walk you through how do you analyze something like this. So this bridge, for example, it has like a big, massive continuity, a continuous truss over here, and a big, massive continuous truss on the opposite side. And then there is an intermediate hinge, and this part is supporting on top of the other two parts. So I want to walk you through how do you deal with a hinge like this? And the answer is very easy. You just separate the two parts, separate the right-hand side and the left-hand side, and deal with the pin or the intermediate hinge as a hinge support, meaning assume from one side, from the left-hand side, two reactions in X and Y direction, just as if this was a hinge support. And then immediately consider action, reaction, take the same magnitude of the forces, flip them, equal and opposite on the opposite side, and this will show you the equilibrium between the two sides. So let's go through this example and see if we can find the reactions and find the internal forces at the pin. So let me go ahead and show you um, the beam we're talking about. So we have here an interesting thing. We've dealt with this um, before. This is a distributed load. There is an internal pin. Part BC is supported by the pin over here and the roller support at C. There is a couple or a moment external load or external couple, 4.5 kilonewton meter. External load, point load, 18. And there is a support at A. Any guess what is the support at A? Well, this is a fixed support. And the fixed support is worth three unknowns or three reactions. Okay, so how do we deal with a problem like this? Obviously, we need to deal with this pin support. And working with it, it's so easy. You just take the right-hand side and separate it from the left-hand side and deal with B as if it was a hinge support. So let me do really quickly. This is the left-hand side. This is the right-hand side. I will quickly assume B to be a hinge support. So I will give it um, force in X. Let's call this Bx. And a force in Y. Let's call this By. So that's the rule. It says deal with it as if it's a hinge support, but very quickly take the same magnitude but opposite direction and flip it on the opposite side of the structure. So you take this force and it's the same magnitude, Bx, and you assume it's going upward, you assume it going downward here, and you call it the same name, it's By. So the interesting thing is when you put the right-hand side and the left-hand side back together, you will see these two equal and opposite forces. They cancel each other. These two and equal forces cancel each other. And this leaves the pin joint in equilibrium the same way we found it. So these forces, when you put them back, they will cancel each other. Okay, so let's deal with the right-hand side free body diagram, and then we'll do the left-hand side free body diagram. Uh, this is joint C. So what's the reaction at C? Because this is a roller support, we have to put one reaction. I will call it CY. The external couple will show up for sure, and this is 4.5 kilonewton meter. Am I missing anything else on the right-hand side? Yes, the point load. So I will put 18 kilonewton. And this is the right-hand side of the problem, right from the intermediate hinge, and it is in equilibrium. Everything here is in equilibrium. So summation of forces in X equals 0, summation of forces in Y equals 0, summation of forces in the summation of moments will equal 0 as well. Okay, let me very quickly here deal with the distributed load and the fixed support at A. Because A is a fixed support, so this will require a reaction in X. I will call this AX. A reaction in Y, I will call this a Y. And because of the fixity, I will put a couple and we'll call it the moment at A. These are three unknowns. I'm not sure how much these forces are, so I will have to calculate them from the equilibrium equation. Now, I'm going to replace the distributed load with a point load. And by now we know the rule. It's the magnitude of the distributed load multiplied by the length of the distributed load. So this will leave us with 3.6 multiplied by 5. This is kilo Newton per meter multiplied by meter, which will leave us with kilonewton. I will do the math really quickly. 3.6 multiplied by 5. This will result in 18 kilonewton. So this will work just for the sake of the reactions, but later on, when we are calculating the internal forces in this rigid body, we will have to consider it as a distributed load. We will talk about this later. All right, so how many unknowns do we have on the left-hand side? 1, 2, 3 at this support A, plus 2 more at B. This is 5 unknowns. Do we have enough equations to calculate the 5 unknowns? The answer is no. We just have 3 equilibrium equations, which is just perfect for the right-hand side for member BC to be able to figure out all the unknowns. So I will solve member, I will say for member BC. I will apply the equilibrium equations. Uh, Taking the moments about B probably will help us get C. So I will take the summation of moments about B for the side that is included in this dotted line. And when I take the summation of moments about B here, it will have to equal 0 because this part is in equilibrium. So what are the forces causing moment about B? Cy is causing moment counterclockwise, so I will consider Cy as positive, multiplied by the distance from C to B is 5 meters. Um, the 4.5 kilonewton meter is also going counterclockwise, so I will add it plus 4.5 kilonewton meter. Is there anything else causing rotation about B? You get to know by putting your finger at B and observing what are the forces rotating about B. You will quickly realize the 18 is rotating clockwise. Clockwise, I will consider it as negative. The force is 18 and the distance between the point load and B is 2 meters. So I will multiply this by 2 meters. When you add up all these moments, the answer has to equal 0. So let's do quickly the math. 18 times 2 minus 4.5. Uh, this will have to be divided by 5. This will result in Cy to be positive 6.3 kilonewton. So what does that mean? What does the positive mean? It means this assumed direction is correct. So Cy is 6.3 kilonewton. So we figured out the first reaction at C, which is what the question is asking. The second thing, the question wanted to know the internal forces at the intermediate pin or intermediate hinge B. So taking the summation of forces in the x direction and equating this to 0, you will realize the only force in x is bx, and therefore bx will have to equal 0. So this guy here is 0, and if we know that bx is 0, that means bx on the opposite side is 0 as well. All right, that leaves us with just by. And you probably guessed it, that first equilibrium equation we used was the moment about B. The second equilibrium equation is the summation of forces in x has to equal 0, and this gave us the reaction Bx. The third equation, I will consider that the summation of forces in y will have to equal 0. So all the forces going up minus all the forces going down will have to equal 0. By is going up, it's positive. I will use by plus Cy is going upward, and it's we know its magnitude, it's 6.3. So I will put the 6.3 kilonewton. And that's pretty much all the forces going up. There is just one force going down, which is negative 18, because it's in the negative y direction. And when you add all of this, it will have to equal 0. And from this equation, I will just quickly do the math. 18 minus 6.3. This will result in By equals 11.7 kilonewton. So By equals 11.7 kilonewton. So the sign is positive. And what does that mean? It means this is the correct direction. By is actually going upward here, and the magnitude is 11.7 kilonewton. Newton. So if we know By here, do we know the direction and magnitude of By on the opposite side? And the answer is yes, absolutely. It's equal and opposite. So if By going upward from the right-hand side of the joint, it's equal and opposite. So it's going downward with the same magnitude, 11.7 kilo Newton. Okay, so now we are starting to realize that the left-hand side is becoming doable now because we know Bx, it's 0, and we know By, it's 11.7. That leaves us with just 3 unknowns at A. So for part A, B, I will consider the equilibrium equations. So what are the equation we want to apply first? I could say, let's figure out the fixed moment MA first. So I will take the summation of moments about the point with the most number of unknowns, which is A. So I will say the summation of moments about A just for that part outside of the dotted line. So everything on the left of the pin will have to equal 0. So first force causing rotation about A is By, and it's going clockwise. So let's consider clockwise to be negative. So this will be negative 11.7. That's the force in kilonewton. I will have to multiply it by the distance from B to A. And if you just add all these distances, you will realize that the summation of all these distances is 10 meters. That's the first force. Um, if you look at the 18 kilonewton, this is the resultant of the distributed load. So that's perfect. I remove the distributed load and I'm going to use the resultant to calculate the reactions. I mentioned before, if we are calculating the internal forces, I will have to consider it as a distributed load, but just for the sake of reactions, this is a something that we can use the resultant for. So the 18 is moving about A in a clockwise direction, same as the direction of the 11.7. So I'm going to subtract. The force is 18 kilonewton, and the distance is the distance from the point of application or the resultant to point A. So do we know where is the distance between the 18 and the beginning of the point load? And the rule says if this is a rectangular distributed load, the resultant is in the middle of the length. So this is 2.5 meter and this is 2.5 meter. So if I want the distance from the 18 all the way till A, I will have to add 2.5 plus 2, and this whole thing would be 4.5. So I will multiply the 18 times 4.5. This is in meters. This is in meters. And it's rotating same direction as By. This leaves us with MA. So I assume that it's going clockwise. So this means that it's negative. And I gave it a name of MA. So this is the unknown moment MA. What about AX and AY? Do they cause moment about point A? The answer is no, because these two forces, they pass through point A, so they don't cause rotation about it. It's only the fixed reaction couple that will be accounted for in the moment equation. So what happens when I add up all these moments? The answer has to equal 0 because this left left-hand side of the pin is in equilibrium. I will quickly crunch the numbers. I will realize that 11.7 times 10, and when you add to it 18 times 4.5, this will equal 198, and it's in the negative sign. So MA equals 198 kilonewton meter, and it's negative. So what does the negative mean? It means the rotation is not clockwise, it's actually counterclockwise. It's opposite to what I assumed. So that's fine. We now know that the reaction couple at A is 198 kilonewton meter going in the opposite of the direction I assumed. So I could just like quickly say I will flip the dimension, I will remove the sign, and I will say this is 198 kilo Newton meter, and it's going counter clockwise like this. So if you leave the sign like this, I will go and check your assumption, and your assumption is going clockwise, and you're saying negative. So now I understand your answer. Or you could remove this and say the magnitude is that much, and it's going counterclockwise. From here, we realize that we figure out the moment, we figure out the reaction By and Bx, which is, by the way, the internal forces at the pin. So we satisfied that part of the question. We calculated Cy. The only thing missing is Ax and Ay. So if this was equilibrium equation 1, I will take equilibrium equation 2 as the summation of forces in X has to equal 0. If you look closely at the left-hand side of the joint, you will realize that AX is will have to equal BX. And since BX is 0, then AX is 0 as well. So this equation will show us that AX has to be 0. So this is 0. This is the second equilibrium equation. The third equilibrium equation, which is the summation of forces in Y, has to equal 0. I will take everything going up as positive minus everything going down and equate that to 0. The first force here is a Y. It's going positive Y, so I'll take it positive. Minus the 18 is going downward, so I'll take 18 kilo Newton. There is By going downward, so I will take minus 11.7 kilonewton. I will just look closely that I accounted for all the forces in Y. So I counted AY, the 18, BY, which is 11.7. That's pretty much everything. So when I add all of it, it has to equal 0. So I'll do the math real quickly. 18 plus 11.7. That means that AY is 29.7 kilonewton in the positive direction. So what does the positive mean? That means this assumption is right. So this means that AY is 29.7 kilonewton. So this shows that we figured out the reaction AY, we figured out the internal forces, we figured out this moment, and we figured out CY. And this is pretty much it. This is all what I wanted to say about dealing with the intermediate support. And I will see you in another video. See ya.